So, hello everyone. Welcome to a late starting class. This is the end of the 9th week. And as we missed one class, this will be the 17th lecture, which will go up on my new YouTube channel. Please like and subscribe. Aileen, please like and subscribe my YouTube channel. Thank you very much. And to all your friends, let's get a nice little pyramid scheme going. Everyone gets 5 people to like and subscribe. I make millions. I lead CSUN. I give you all A's because I don't need CSUN anymore. It'll be a wonderful thing. Let's get it started. But other than that, let's go ahead and continue with where we left off. We have been working on confidence intervals. And last time we went through 8 of them. 1, 2, 3, 1, 2, 3, 4.
Professor,
Yes.
you wanted me to remind you that last time we didn't get to finish the last one. You didn't tell us like when to use it.
Gotcha. So let's see what the last one was.
It's usually like you give us like when it's greater than 40 or 15.
I think here it is. Okay. So the last one was the 2 sample mean when sigma 1 and sigma 2 are both not known, correct? That would have been from chapter 21, which means I got to put
Hey, Professor,
yes.
you're not recording.
Oh, yeah, I am.
Oh, shoot. Sorry. It didn't show up on my screen. My bad.
Unbelievable. Just can't find good help these days, can ya? No, except for my dad. He's good help. But other than that, and Aileen, you're pretty good too.
Oh, thank you.
You're welcome.
Casserole. I hope that's all right.
Casserole. I'll have some casserole. That'd be wonderful. So chapter 21 was our last confidence interval. And this one was 2 sample means because, sorry, 2 sample means when sigma 1 and sigma 2 are not known. So we had the formula x1 bar minus x2 bar plus or minus t star squared of s1 squared over n1 plus n2 squared over n2. I'm holding it up just to remind you what it was, but you should have had that copy from last time. And this is used when we do not know what the standard deviations are. Now, when you go online or you use your calculator to use the example of 2 sample means when sigma 1 and sigma 2 are not known, let me just show you what pops up. So first, you're going to have something that looks like this. It will be called, on your calculator, it will be called the 2 sample t-test. Or actually, this is the confidence interval. So let's go down confidence intervals. This is the 2 sample t interval. And when you click on the 2 sample t interval, you'll have a lot of stuff to input. You can either use the data itself or you can use the stats themselves. Now, sometimes you'll have the data and sometimes you'll have the stats, so you should know how to use both. But you'll notice that you have to input, if you're going to use the stats, you got to know x1 bar and sx1 and n1 and x2 bar and sx2 and n2 in the confidence level. And that all makes sense because those are the things that we don't, that we have in the formula. X1 bar, x2 bar, t star, s1, s2, n1, and n2. So it makes a lot of sense that you got to put those things in so your calculator can calculate it for you. But then there's one last thing on your calculator. And the one last thing on your calculator is the bottom line of the calculator, which says pooled, no, or yes. So what does that mean, pooled, no, or yes? It means the following. Sometimes you don't know sigma 1 and sigma 2, but you happen to know that they're equal. You might not know what it is, but you know that they're equal. And in that situation, we pool them together. So if in the problem you are given the additional information that you happen to know sigma 1 and sigma 2, then on your calculator or on the computer, whatever you use to do this particular example, you will pool them together. If you do not know that they are the same, then you will hit pooled no, and you will not pool them together. Okay, so the only time you pool them is if you are given that little bit of extra information that says, hey, they're the same. If you're not given that anywhere in the problem, don't do it, okay? And I didn't fill in the other things, S1, X1 bar, and so on yet, because I just haven't had time. I'm always doing something and I'm always running out of time. But again, when is this used? This is used when you have two samples and two sample means, and you're coming up with a confidence interval for their difference. Okay, X1 bar minus X2 bar. So what I want to do now, for the rest of today, we have an hour, 10 minutes or so, or an hour, yeah. What I want to do today is I want to do lots and lots of examples. Oh yeah. So we got to put in when you use this. That's what you were talking about when you said the information, correct? So star, okay, use when they both come from an SRS. As always, they have to be from an SRS. They are both normal. Okay, they are both normal. In terms of the size, the book doesn't specifically mention anything about their size, but I would have to imagine that it's the same. Here we go. So they're both normal, and or if not normal, but moderate, and I'll hold this up before, but moderate skewness with no outliers, then N1 plus N2, the sum of the samples should be greater than or equal to 15. Or if not normal with strong skewness and no outliers, N1 plus N2 should be greater than or equal to 40. So I'm going to hold that up so you can copy it. And I'll try to be relatively okay. Is that good? My hands are hurting, so I hope so. Okay. So at this point, we're now going to do a bunch of questions. Oh yeah. Okay, so I'm going to pick question. Essentially, I'm going to pick a question from each situation, and hopefully it'll be obvious as we solve the question which situation it's from, and then how to go ahead and solve it. Okay, so here we go for an example. A 2011 NBC News survey, and what I want you to do is I want you to stop me as soon as I say something which you believe is mathematically relevant to the problem. So a 2011 NBC News survey found that 80% of a sample of 4,500 American teens said they owned an MP3 player such as an iPod. Assume that the sample was an SRS. Now, no one stopped me so far, but there was a lot of information in that paragraph.
Is it 80% was the sample proportion?
Okay, so yeah, this problem is on page 369 of this book, which I hope is, I mean, this is the correct book. I know that now, but I hope it's the one that everyone has. I don't want to type it out. That would take too long, but it'll be on video and on YouTube. You can watch and you can pause it. It's amazing. So again, it says a 2011 NBC News survey found that 80% of the sample. So that is the sample proportion. It's 80% of the sample, not 80% of the entire world, but 80% of the sample, which means how do we label that 80%? Page 369. What is the labeling for the sample proportion? What symbol do we use for the sample proportion? No, X bar is the sample mean. It's 16.23. Oh, actually, it's just before 16.23. Just before 16.23. There's a 4 lines that references 23 through 26. It's right, right before that. So X bar we use for the sample mean, but this is a sample proportion. Yes, p hat. So p hat is equal to 0.80, and it was a sample of 4,500 American teens. Well, 4,500 is certainly numerical. So what do you think 4,500 should be labeled as? Not everyone at once now. I can't hear over the noise. N, excellent, right? So then the sample size N is 4,500. And we're told that the sample is an SRS. We're told that the sample is an SRS. Why is that important that it's an SRS? Because one of our conditions for all of these formulas is that things come from an SRS. Okay, now if they don't tell you that it's an SRS, just assume it is, unless that's the point of the question. Or unless, yeah, p hat is 0.8. Unless they tell you that it's a convenience sample or a voluntary response sample or a stratified random sample. If they don't tell you that's one of the others, I think you're gonna normally assume it's an SRS. Okay. So the question is, what is the 90% confidence interval going to be? We're looking, okay, we want the 90% confidence interval. So remember, in the very beginning, we had 4 questions. Question 1, does the problem deal with means or proportions?
This one uses proportions.
Proportions. Does the problem deal with 1 sample or 2?
1 sample.
1 sample. I'm going to skip question 3, which was if it deals with means, because it doesn't. But if it deals with proportions, is the sample small or not? Is it a small sample or is it a large sample? Well, it's 4,500, correct? Right? 4,500 people. Now, 4,500 might be large, it might not be large. But remember what we need to use the formulas. If you go to the 1 sample proportion, where the sample size is large, the very first one that we did We use this when n times p hat and n times 1 minus p hat are both greater than or equal to 10. Well, what is n times p hat? What is 4,500 times 0.8? Is that greater than or equal to 10? Without even calculating it, I hope you know that it is. 80% of 4,500 is going to be 3,000 something. But what about 1 minus p hat? What about 20% of 4,500? What's 20% of 4,500? Well, even 20% of 4,500 is pretty big. It's almost 1,000. So both n times p hat and n times 1 minus p hat are greater than or equal to 10. So yes, the sample is large. And I can use the very first one, which is the one sample proportion where the sample size is large. And the confidence interval is p hat plus or minus z star, the square root of p hat, 1 minus p hat over n. This is the formula. Now, how many of these things do we know in this problem? Do we know p hat?
Yes, isn't it 0.8?
It is 0.8, and in fact, it appears 3 times, so it's a pretty good thing that we know it. Do we know n?
Yep, 4,500.
4,500. Do we know z star?
Oh my gosh, yeah, it was on the paper. 1 second, let me find it.
Anyone remember what z star is for a 90% confidence interval? It's one of the ones you should memorize, one of the big 3.
Isn't it 2?
It is not 2.
1.64.
It is 1.645. Okay. The question does not say it's a proportion. I mean, does the word actually? No, the question never says it's proportion, but it says 80%. 80% tells you that it's a proportion. Doesn't say the word proportion in it. You're not always going to have that. Those lights are really bright back there, but it doesn't automatically. No, it's okay. It's okay. Don't worry about it. Don't worry about it. Fine. It's okay. Just do your thing. Do your thing. It's okay. I'll just try to. I'm a pretty big guy, so I should be able to block this light out without a problem. Oh, okay.
It's okay. I made a casserole in the dark.
Okay. Ooh, a dark made casserole. That sounds messy. But anyway, so it does not say that it's a proportion, but it's 80%. 80% tells you that it's a proportion. We're not looking for the average of something. We're looking for what percent of something. What percent of teenagers own an MP3 player, such as an iPod, etc. So we have everything we need. You plug everything in, you get the answer. The rest of the problem is math, plugging it in. I want to make sure that you know how to set up these problems. So let's do another example. I'm now going to go to another chapter and pick another example. Okay, here we have one. And this, if you want to follow along at home, this is on page 407. Do I want to use this one? Hold on. Yeah, why not? We don't have to go in order. Okay. So this is on page 407. It says the Abecedarian project was a randomly controlled study to assess the effects of intensive early childhood education on children who were at high risk based on several socio-demographic indicators. The project randomly assigned children to a treatment group, which was provided with early educational activities before kindergarten, and the remainder to a control group, okay? The control group means don't do anything. The treatment group means do something, okay? A recent follow-up study interviewed subjects at age 30, and compared the college graduation rates, basically earning a 4-year degree. Here's the data for the two groups, group 1 and group 2. So group 1 was the treatment group, and group 2 was the control group. Group 1 had 52 people. Group 2 had 49 people. I'm going to hold this up in a second. The number of successes in the first group was 12. The number of successes in the second group was 3. So here's the data. we have two groups, the treatment group who received all this education and the control group that did not. There were 52 people in the treatment group and there were 49 people in the control group. And of the treatment group, 12 of them succeeded. And of the treatment group, 12 of them succeeded. And of the control group, 3 of them succeeded. This is the information. And what we're looking for here is a 90% confidence interval on the difference. We want a 90% confidence interval on the difference because we're trying to check whether or not one was better than the other. So a 90% confidence interval on the difference. Okay. That was like 10 seconds, so I hope that's enough. So let's go to our questions. Question 1. Does the problem deal with means or proportions? Are we interested in averages or are we interested in percents? We are interested in percents. What percent of the first group compared to what percent or proportion of the second group? This is a proportion problem. Question 2, does the problem deal with one sample or 2?
2.
Okay. If it deals with proportions, which it does, is the sample small or not? Now, if we go to the 2 sample proportion formulas and we look at where the samples are large or not large, let's see what the conditions are. We need N1 P1 hat, N1 1 minus P hat, P1 hat, N2 P2 hat, and N2 1 minus P2 hat, all to be greater than or equal to 10. Well, let's see if we have that. First, let's calculate P1 hat. What is P1 hat equal to here? And by the way, just so you know, another way of thinking of N1 P1 hats and N2 P2 hat and N1 1 minus P1 hat and N2 1 minus P2 hat, if you don't want to think about it in terms of math, essentially it means, yes, exactly, 12 over 52. Essentially what it means is the number of successes and failures for each case must be greater than or equal to 10. So if you don't want to think about it in terms of numbers, you can think about it in terms of successes and failures. The number of successes and failures for each one must be greater than or equal to 10. So P1 hat is 12 over 52, which, as was pointed out in chat, P1 hat over P2 is about 0.2308. And P2 hat is going to be what over what? Right? 3 over 49, which is 0.061. But even if we don't do the math, let's just think about that again. How many successes were there in the first group? 12. How many failures were there? Well, there's 42 people. They weren't all failures. Right? There's 40 failures, right? 52 people, 12 successes, 40 failures, correct? Both greater than or equal to 10. Awesome. How many successes were there in the second group? Uh-oh, not greater than or equal to 10. Can't use it. Can't use it. So let's go to the other one. 2 sample proportion where the samples are not large. It says use this when those 4 things are not all greater than or equal to 10, which they're not, but N1 and N2 are each greater than or equal to 5. Do we at least have that condition that N1 and N2 are greater than or equal to 5 here? Yes, by far, right? 52 and 49, certainly. So that's the one that we're going to use. Okay, so let's see what we have to calculate here. The first thing I need is P1 twiddle, right? P1 twiddle or P1 tilde. Based upon the formula that I gave you last time, which hopefully you have in front of you, because that's what this is. This is just looking at formulas and plugging things in. Nothing to memorize, just plug things in. What is P1 twiddle equal to in this example? What over what? Look at the formula. I gave it to you last time. Hopefully you still have it. What is P1 twiddle equal to?
Is it x1 plus 1 over n1 plus 2?
Excellent. X1 plus 1 over N1 plus 2. And what is X1 in this example?
The number of successes in one, which would be 12.
So what's the total for the numerator? What's the total for the numerator?
13,
13. Excellent. What's the total for the denominator?
54.
So P1 twiddle is 13 over 54, which as a fraction is about 0.2407. What is P2 twiddle? What is P2 twiddle?
It's 4 over 51.
4 over 51, excellent, because it's 3 plus 1 over 49 plus 2, which is what? Approximately, this is just pulling it to a calculator again. What do we get? Not everyone at once, please. Anyone?
0.078.
0.078 approximately. I was asking for P2 twiddle. What else do we need in the formula? We need Z star. What is Z star equal to?
Is it
1.96? I don't think so. Not for a 90% confidence.
1.645?
1.645 is what we get for a 90% confidence interval. So what's the formula that I gave you last time?
The P tilde 1 minus P tilde 2 plus or minus Z star times the square root of P1 tilde time in parentheses 1 minus P tilde 1 and then divided by 1 N1 plus 2 and then all of that plus P2 tilde times in parentheses 1 minus P2 tilde parentheses N divided by N2 plus 2.
Could have said it better myself. What I'm gonna do here is do the calculations, but hopefully you can do them yourself as well. Again, it's just plugging things into a formula. So I get 0.162 plus or minus 0.114. And that gives me the following interval from 0.048 up into 0.276. So if you trust me that on my math, this is the final confidence interval. You can always do it later, plugging everything in, but write that down because we're going to analyze it. The confidence interval says from 0.048 to 0.276. The question is, what can we conclude? Is there a difference between the two groups, or is there not a difference between the two groups, and why? Yes, Sydney, 0.048 to 0.276. So the question is there a difference between the two groups, or is there not a difference between the two groups, and why? What's the difference numerically? I'm asking wrong. I'm just asking what it is, huh?
Wait, we're talking about the numbers that Sydney put in the chat, right? The
Well,
point.
that's the confidence interval, right? The confidence interval says that it's from 0.048 to 0.276. That's what I got. That's what she got, right? We got two people get the same thing. Let's assume it's correct. The confidence interval is from 0.048 to 0.276. The question is, how do we get two numbers in calculator? The plus or minus, right? It's P1 hat minus P2 hat minus the big square root, and P1 hat minus P2 hat plus the big square root. So when you subtract, you get one number. When you add, you get the other number. So now we have these two numbers. We have this confidence interval. The question is, what do I conclude from the confidence interval? Is there a difference between P1, the treatment group and the control group, or is there not a difference between the treatment group and the control group? Okay, if there is a difference, tell me why there's a difference. Just because our sample proportions are different doesn't mean there's a difference. You know, in real life, you're always going to have some fluctuation that comes from real life. We want to have statistical evidence that there's a difference. And the question is, do we have that statistical evidence or do we not have that statistical evidence? What are you confused? Talk. Is your mic working?
I have a question. I think I'm a little confused.
Okay.
If this, I'm probably confusing this with something else, where it's statistically significant if it's like less than 5%. Is that?
No, so that's okay. So that's about hypothesis testing, which,
Okay.
which to be honest, is the better approach for asking a problem like this. Okay, if you were trying to determine, is there a difference between these two things? Hypothesis testing is certainly the way to go. But we did go that way. We went the confidence interval approach. And the question is, what can we conclude from the confidence interval? Is there a difference or is there not a difference? So we're not using the whole 5% thing. That's for hypothesis testing. We're using something else.
Okay.
The answer is, without me telling you what we're using, the answer is by looking at this confidence interval, can we conclude that there's a difference between the treatment group and the control group, or can we not conclude that there's a difference between the treatment group and the control group? That's what I'm asking. Can we conclude it or not? When I look down, I'm staring at 0.048 to 0.276. I'm looking at those two numbers. And that's my confidence interval. From that, and from that alone, nope, nothing to do with that. From that and from that alone, the question is, can I conclude that there is a difference or can I not conclude that there is a difference? The whole 5%, that's for hypothesis testing. We're not using any of that. This is the confidence interval, right? We got a confidence interval, nothing to do with hypothesis testing. But yet I can make a conclusion from my confidence interval, just like I can make a confusion from my hypothesis test. Bro, I need a oh, I'm sure I have one around here somewhere. So
Yeah, I'm gonna guess, but I'm pretty
I
sure.
want you to guess, and I want to. Hopefully you guess the right thing. Go.
Oh, I don't think it's right, but because they're not, because it's not exactly like 90% of them, 90% of all your samples or whatever will fall into that, right? But you're not like 100% sure that's gonna fall into there, into
Right.
that little thing. So yeah, there's a difference. I don't know. I
It's
don't
okay.
know.
I wasn't. I don't mind if you're wrong. In fact, being wrong is the surest indication that you have something to learn. I love it when my students are wrong. If you're right all the time, yeah, it's great, you're all right, but you're not learning anything. Can I move backwards? I don't know, I can move backwards. I don't know. I don't know what's forward. That's kind of strange, but what does confidence interval mean again? So it means one thing rigorously, but the way we use confidence intervals is a little different. In this case, I am 90% confident that the true difference in the values of the proportions for the treatment group and the control group are between 0.048 and 0.276. Not that it increases by 4.8 to 27.6%, that the difference, well, I guess, okay, well, okay, I guess, yeah, if the difference is that, fine, okay, good. All right, it's another way of thinking about it. Yes, we are 90% confidence that the program increases the proportion of high-risk children who earn a 4-year degree by age 30 is between 4.8% and 27.6%. We are 90% confident the true value falls in there. Therefore, do we conclude, based upon the data, that there is a difference between the treatment group and the control group? Because remember, we don't know where between 4.8% and 27.6% it lands. So any of those is as equally valid as any other number. No, nothing to do with the size of the intervals. What number is conspicuously absent from that confidence interval? 4.8% to 27.6% does not include what number? It does not include 0%. 0% says there's no difference between the two groups, right? That the increase is 0. This interval does not include 0. I'm essentially 90% confident that 0 is not in there. In fact, my entire interval, those numbers, they're all positive. So I'm 90% confident that there's an increase. But if 0 wasn't that confidence interval, and any number in that interval is as valid as anything else, not because it's not a possibility. This is only a 90% confidence interval. It's still a possibility, but within the limits of my confidence, it's not a possibility. It's got to be between 4.8 and 27.6. I don't know where, but any of those numbers are greater than 0. And therefore, I am essentially 90% confident that it increases the likelihood, the proportion of students who graduate.
So if the interval were to include, wait,
If the interval were to include 0,
okay,
then I could conclude that there's an increase. Even if it went from negative 0.1 to 80, something strange like that. Even if it was hugely on the positive side and just barely into the negative side, I can't conclude it because 0 is a possibility like any other number. But since it does not include 0, since all the values are positive, then I can use the confidence interval to say that I'm 90%, probably more than 90%, because 90% is only at 4.8, right? If I increase that to 95%, maybe even then it would include 0. Or I can kind of keep changing my confidence and see how close I can get to 0 without hitting it. Maybe it's even 99%. I don't know. You got to check the numbers. But the point is that 0 is not in there. And because 0 is not in there, I'm 90% positive that it's not 0. More specifically, I'm 90% positive that it's a positive, 90% certain that it's a positive number. And as such, I'm going to conclude that there is a difference. And if I were to use hypothesis testing for the same scenario, I would have come to the same conclusion because confidence intervals and hypothesis testing almost always overlap in terms of the conclusion that you will make. Does that make sense? I am 90% confident. I am 90% confident that the true difference in proportions is between 4.8% and 27.6%. In other words, not 0. Because if the difference was 0, then there's no difference. Right? There's no difference. How you can conclude that then the treatment group has any effect. But I'm 90% confident that it's not 0, which means I'm 90% confident, more than 90% confident that there is a difference. Does that make sense? So confidence intervals can be used in place of hypothesis testing, but hypothesis testing is still what you want to use as a general rule. So let's do another confidence interval. Again, the first thing we always do is ascertain which confidence interval is appropriate and then plug things in. But at the end, we also want to interpret the confidence intervals. So let's do the following. So let's take a look. Let's do the following example. This will be example on page. Actually, you know what I'm gonna do for this one? It's on page 440, but I also happen to know that it is that I used this example earlier today in my other class who uses the other book that we've been using. So I'm going to load that up just so I can share it. But it is in the book on page 440. So let me find it here. Where are you? Here we go. Okay, 1 second. Okay, I'm going to share my screen. So this was not here. This was. No, wait, it was there. It was that one. It was that one. Okay. So on page 440, we have the following question. Does the expectation of good weather lead to more generous behavior? Psychologists studied the size of the tip at a restaurant when a message indicating that the next day's weather would be good was written on the bill. And here are the tips from 20 patrons, I think it's patrons, measured in percent of the total bill, 20.8%, 18.7%, 19.9%, and so on. We will estimate the mean percentage tip mu for all patrons of this restaurant when they receive a message on their bill indicating that the next day's weather will be good by giving a 95% confidence interval. So we are looking for a 95% confidence interval. Well, so the first thing we do, we go to our questions. So question 1, does the problem deal with means or proportions? So even though these are all percents, 20.8%, 18.7%, what we're after is the average percent. Okay, it says here, we're looking for mu, the average percent. The mean percent. So this is actually a mean problem, not a percent problem. Even though it says percents, but we're looking for the average percent. So it's a mean. Does the problem deal with 1 sample or 2 samples? No, it's only 1 sample. The whole thing, both lines are just 1 sample. 20 people, 1 sample. Okay, it's not the top line and bottom line being different. It's just here's tips from 20 people. So this is 1 sample. If it deals with means, which it is, do we know sigma or not? Do we know sigma? Does it say anywhere in the problem what sigma is? No, it does not. Okay, so let's find the one that's appropriate. We're looking for a one sample mean when sigma is not known. Here we go. One sample mean when sigma is not known. And what do we have? We have x bar plus or minus ts over the square root of n. X bar is what? What is x bar? Sorry, what is x bar? What does x bar always stand for?
Sample mean.
Sample mean. What does S stand for?
The sample size.
No, that's n. N is the sample size.
My bad. It's sample standard deviation.
Sample standard deviation. And what is T star? T star is like Z star, only it's T. But in order to calculate T star, if we were to go to a table of values, what would we need to recognize about this sample in order to calculate T star? This is on page 440 in my book, or 454. What's on 454? No, I have page 440. When you look at the T table, we did this last time. When you look at the T table, there's numbers on the left. Those numbers are the degrees of freedom. Yeah, numbers are degrees of freedom. So how many degrees of freedom do we have?
19.
19. The number of data points minus 1, 19. But what I'm going to do is I'm going to go to Crunch It. And what Crunch It can do is a few things. So let's actually go through it. I know you hate Crunch It, or you hate the recognition that Crunch It's out there and you don't have it. Okay, I know. It's horrible. But let's instead of going right to the answer, let's do a few things. First, let's do descriptive statistics. What do I want here? No, that's not what I want. Okay, let's find what I want. I want to calculate the mean. So that's not those. It's not those. I would think it's just descriptive statistics, but maybe it is. I don't know. No. Oh, okay, there. I just said calculate. So the mean x bar, the sample mean, x bar is equal to 22.21. And the sample standard deviation is 1.963. And the number of degrees of freedom, as we already mentioned, it's not listed here, is 19. We don't need the other stuff, the min, the Q1, median, Q3, max. The 5-number summary is not going to help us here. Okay, but it does give us the mean and it gives us S. So now I'm going to go to my statistics. And because this is a T star problem, I'm going to go to T. And because it's a one sample problem, I'm going to go to one sample. And I have two possibilities, hypothesis test or confidence interval. I'm going to choose confidence interval. Did it say what confidence we want here in the problem? Does it say the confidence? I forgot. It says 95% confidence interval. Yes, 95%. So 95 confidence interval. It needs to mean no, my sample is. This is the percent column. So if I have multiple columns, it says, hey, which one? It's the percent column. And then I say calculate. Notice that it gives me the sample mean again, 22.21. It doesn't give me the standard deviation. It gives me the standard error, but we got the standard deviation the other way. The degrees of freedom is 19, and my 95% confidence interval is 21.29 to 23.13. Had I gone ahead and plugged things into the formula, I could have done it that way. And the only problem is I would have to know T star. And the question is, how do I calculate T star based upon my data? How do I calculate T star? The standard deviation. Okay, so it's a good question. I'll show you how to get it. Basically, the sample error is this. The sample error is S over the square root of N. So when they give you the sample error, all you have to do is multiply that by the square root of 20. And that will give you the sample standard deviation. So, I mean, let's just show it that it gets the same 1.963 that it did before. If I take 0.4388 and I multiply it by the square root of 20, I get that 1.96 a bunch of other numbers. We see that I do get the same value that I had before. Okay, so it doesn't give you immediately the standard deviation, but it allows you to find it. What it does not give me is it does not give me T star. So let's see if there's a way for me to find T star here. That wasn't it. Well, T star doesn't come from the data, right? T star comes from a table. So here's the student's T. And we want a 95. Okay, so first of all, degrees of freedom. We have 19 degrees of freedom. And we're looking for a 95% confidence interval, correct? The degrees of freedom is one less than the sample size. So if the sample size is 20, then the degrees of freedom will be 19. And if it's 95% confidence, if the middle is 95%, that gives us 2.5%. So I want 0.975. I want 97.5%. And that gives me a T star value of 0.829. So Crunchit's amazing. It gives me everything I need. However, for those poor people like Sydney who doesn't have Crunchit, and it can only sit there in jealousy of the amazing features that mathematicians around the world have access to. For the rest of you, there is the internet. So let's do it on the internet. You know, I mean, obviously, I don't know Yahoo, but obviously, ooh, is there a debate tonight? What's happening right now, huh? Well, luckily we're in math class. So started at 6. Well, whatever. Let's go to a T table. And so let's look at a T table. Let's look at this one here, maybe. Okay, we got a T table. So we want 19. Ooh, damn, looks like my boy Snowden has an out. Snowden, how do I know that name? See the guy, he was the leaker, right? Yeah, how long has he been in Russia now? Like 10 years? How long has that been going on? Time flies when you get old, guys, I'm telling you. I think things were like, oh yeah, that was like 2 or 3 months ago, and it was really like 2 or 3 years ago. It's just undisclosed location for now. Well, some of us know where he is, but you know, we got to keep it secret from the rest of you. Anyways, so degrees of freedom, 19. And we want a one, actually here, we want a 2-tail 5% or 1-tail 2.5%. And here we go, 2.0930, which was the same. Where was it? Wait a second. What do we get here in Crunchit? Oh, actually, what I wanted was this. I'm sorry, I looked at the wrong thing. That's what I wanted. I apologize. I didn't want to say what's the probability of being less than 0.975. I said what number gives me 0.975 less than it, and that is 2.093. And if I go to this table here, I get for 19 degrees of freedom, I get 2 point. So why is it 0.975 again? Because remember, we have a shape that looks like a bell curve. It might be a bell curve, it might be close to a bell curve. And we want 95% to be in the middle. We want a 95% confidence interval in the middle, which leaves 5% for the wings in total, right? And therefore 2.5% in this wing and 2.5% in this wing. So if I take this point right here that I'm looking for and I go left, that means there's a total of 97.5% to the left of it. So I'm looking for the points such that 97.5% is to the left of it. And if you look at the crunch it thing, okay, being less than 2.093 gives me 0.975. The probability being less than it is 0.975. So you can see the table works, crunch it works. There's multiple ways of getting what we need. The TI-84 does it. A quick Google search for a T distribution or a T calculator or something like that will do it. There's many options that Sydney can use. Meanwhile, those of us who have the luxuries of like having, you know, yachts and helicopters and private jets and crunch it, we can just use those instead. Does that make sense so far? So notice all these examples is just asking yourself the 4 questions. It's like Passover. Ask yourself the 4 questions. Find out which example you're going to be in. When you get to that formula, when you get to that situation, make sure you understand how to get all of those things. And then when you get all of those things, then plug them in, take out a calculator or use Google or use something to get it. But at the end, you now want to interpret the confidence interval. You want to say, okay, what does this confidence interval mean? What does it mean that I'm 90% confident that something is between this number and this number and so on? Okay, so the answer is essentially check if the number that you're questioning falls inside the confidence interval. If you're checking whether or not there's a difference, i.e. if the difference is 0 or not, does 0 fall in the confidence interval? If you think one is 10% more than the other, does 10% fall in the confidence interval, right? It's the number that you're after. Does it fall in that interval or not? You're going to use that to base your conclusions on that. So I am 97%, 97%. I don't think it was 97%. I think it was 95%. Right? I am 95% confident in this example that the true value of tip percentage when you give a message that it's going to be nice the next day was between 21.29% and 23.13%. Right? Because that's what this problem was about. What do people tip when there's good news? Can you repeat that? I write slow. I'm sorry. Mea culpa. I've always talked too fast in my life. I have a problem. I always have so much to say and I want to say it all, and sometimes I stumble over my words. You know, it's a problem. Those were the edges of the confidence interval, were they not? Right, when we got our confidence interval here, I think we did it on Crunch It. Did we do the confidence interval on Crunch It? If not, we should have. T, one sample, confidence interval, 95%. Right, so here's our confidence interval, 21.29 to 23.13. So we are 95% confident that the true percent of tip that people give when there's a message that it's going to be nice outside the next day is between 21.29% and 23.13%. If when I give a message that it's going to be rainy and horrible the next day, if that overlaps with this confidence interval, right? If I do a confidence interval for that case and a confidence interval for our case and it overlaps, what do you conclude versus if it does not overlap? What do you conclude if it overlaps or does not overlap? So if it overlaps, we would conclude not that there's no difference, but we would conclude there's not enough evidence to suggest that there's a difference. Right? You see the difference? It's a nuance, right? We can't conclude that there's no difference, but there's not enough evidence to conclude that there is a difference because we don't know where in that overlap we are. So for all we know, we're right there where it actually overlaps. We don't know if it's over here, and so on. But if it does not overlap, then we're 95% confident that the true value of this is greater than the true value of this and that there is a difference. Yes, that's exactly it. That's exactly it. Except I would spell Gib with only one E, but other than that, it was wonderful. And I would write out the word you, but that's just a generational thing. And I would, actually that's pretty much it. Can't really think of any other criticisms. So does that oh, I am an asshole. Anyways, does that make sense? Any questions on this? Because we are done with confidence intervals, which means next week we do hypothesis testing. And we go through all the examples of hypothesis testing. And then we do a little cleanup. We see what we missed. And then we'll be ready for the second test. So it'll probably be in a couple weeks. Can you calculate the first example we did? I want to make sure I got the right answer. The very first example. Yeah, I can do the quick, hold on. Yeah, you need practice. That's what homework's all about. That's exactly it. So 0.8 times 0.2 divided by 4,500. Take the square root of that number, multiply it by 1.645, do 0.8 minus that number. It's 0.79. Okay, Oliver, thank you. 0.79 to 0.81. So that was a pretty small confidence interval, right? We got 80%. Notice how in the first example, I didn't actually do the math before, but I'll do it now because you know what? There's something to be said from it. I did the math and I got 0.79 to 0.81. So the center was 0.8 and we went 1% left, 1% right. Very small confidence interval. Why do you think it's such a small confidence interval in that example? Why do you think the first example is such a small confidence interval? Yes, exactly. It's a huge sample size, right? The bigger the sample size, the smaller the confidence interval is going to be, right? It's huge. Yes, it's a huge sample size. So the confidence interval is very small and we're really tight around the value. So I'm 90% confident that it's between 0.79 and 0.81, right? The bigger the confidence, the bigger the sample size, the more confidence you get. Does that make sense? I wish the homework, here's the thing, Sydney. The homework might be phrased problematically sometimes. And when it's phrased bad, sometimes it's hard to really understand what they're asking. I don't like Launchpad, but don't fall into the trap of thinking that it's simple because you're following along with me doing the answers. Because if you sat down to do the problems yourself, chances are it would be a lot more problematic because you're watching someone who knows what he's doing do it. And you're saying, okay, yeah, that makes sense. Oh, yeah, that makes sense. Oh, yeah. Oh, okay, I got this. If I then go, okay, now you do one, you'd be like, what do I do? Because it's the practice that you do that makes you internalize it. When you watch me do it, you're like, okay, I have a grasp of it. As Ingrid said, I think it's solid. I just need practice. That's for everyone. No matter how much you think you know this, any one of you, those who are talkative or those who are not, those who are, I mean, all of you. Chances are, you sit down to do one yourself right now, chances are you will not succeed because you haven't struggled to do it yourself. And when you do that and you get a few wrong and you figure it out and then you get it, then everything changes. When's the next quiz or test? Fantastic. We should have a quiz in confidence intervals. That's a great idea. Okay. And it's not because she said anything. Don't blame her. She's an amazing person. Yes. Yes. Quizzes are good. Quizzes forces you to study and to internalize so that you do better on tests where it really counts. Quizzes are wonderful. But no, we're not going to have a quiz because Math 140 doesn't have any quizzes. So I was going to do it, but then I'm like, I don't want to grade that. So we're not going to have a quiz. No, we're going to go right to the tests. Okay. Sydney, you have, what's today? Thursday? You have essentially 48 hours to get me that. Do you think you can get me that in 48 hours? Because if you're saying you're going to get it to me after I start my diet, you are trying to sabotage me. And that is not good because I don't know anyone on this planet that can resist orange creamsicles. Aileen, can you resist orange creamsicles that they're put in front of you?
I cannot.
See, she can't either. Okay. So what will the test be on? It'll be on confidence intervals. It'll be on hypothesis testing. That's it. Those two concepts, confidence intervals and hypothesis testing. So it'll be on essentially chapters. Hell's table of contents here. Here we go. It'll essentially be on chapters 15 through 21. 15 through 21, which sounds like a lot. Oh my God, Ani, what is that? Is that your brain exploding? Is that what that is? That's awesome. How's the casserole doing? They're asking. How's the casserole?
It's coming.
This is why I don't cook. She's been there for like 9 hours, okay? Fast food is fast.
Has this class been 9 hours?
I don't know. It feels like that. I don't know. It's just.
Well, don't worry. Casserole's coming soon. It's extra cheesy for you.
Oh, wait. It's for me too?
Yeah.
Hell yeah! I got some casserole coming.
I accidentally made all of the pasta, so I need you to help me.
I will help. I promise. I will help. This is one thing that I'm really good at. I will help. There's only so much variety in fast food. There's only so much variety in fast food. Oh, yeah, you're right. But then you do it, and the next day you do it all again. It makes sense. Anyways, so confidence intervals and hypothesis testing is 15 through 21. But the way they do it in the book is they kind of just do a whole chapter for essentially like 1 or 2 formulas. So essentially, there's stuff in those chapters that are not on confidence intervals or hypothesis testing, but I'm only going to ask on confidence intervals and hypothesis testing. So all the other stuff we will do afterwards. We'll do a cleanup of those chapters. Will it be possible for you to put some review questions before the test? I guess I can do that. I guess. Okay, fine. Oh my God, yes, a study guide. A study guide. Yeah, I can do that, I guess. I can do that, I guess. I can tell you exactly what you need to know. Essentially, I hate doing that in general, but with this, the format of this class, I don't mind because I am, and it's your with an E, just so you know. But anyways, it's the format of this class, and especially my screw up with using the wrong book and whatnot. I'm trying to do whatever I can to help you guys out in that regard. I'm not a big fan of study guides, but I will do it this time. Tell you exactly what you need from each chapter. I'll go through it all and say, this is what you need, this is what you need, this is what you need, and so on. And, but it's not going to be for a couple of weeks because next week is hypothesis testing. So I'm going to have some casserole. And no offense, but and the formula sheet I will also put up on Canvas. I haven't done it yet, but I will, I promise. I wanted to finish today, the last thing. Sorry, I have a, yeah, whatever. Anyways, get out of here. I'm gonna eat. You can watch me eat, I don't mind, but I I will. What do you laugh at?
He's gonna do an on the spot mukbang for all your students.
Good night, everyone. I will see you all on Tuesday. So keep the faith, brothers and sisters. Love you all.
Professor,
Oh, you're here. I got you. And it was someone else. Who was it? Oliver. I got you as well. Yes.
did you? I came in late because I had to do
Great.
the presentation thing.
Okay, wait, I gotta put up.
I mentioned that last time.
Hold on. Oliver, Grace, and Muyua. Okay, I'll get you up. I'll get you up.
Bye, Professor.
Okay, thank you.
Birthday.
Good night.
Okay, guys. Have a good night.
Happy birthday.
Thank you. Thank you. Appreciate that. Thank you, guys.
Hey, Professor. I got a few questions about the homework's grading scale because I've seen that our exams are worth 100 points each, and
Yeah.
it seems that our exams are worth 100 points.
Don't worry about any grades that you're getting on Canvas or a Launchpad. Whatever grades they're currently giving you is irrelevant. I will put everything in the appropriate category and give everything the same weight before the end of the semester. If that's what you're.
So do the homeworks have the same weight as the exams?
No, I mean the syllabus. The syllabus should say what it is.
Yeah,
It's
because
it's not as much.
okay, because yeah, I've been stressed about my previous homeworks grades. I saw that you updated the deadline because you had mentioned that on Tuesday, and I'm like, oh, that's great. And so I looked at it on Wednesday, and I'm like, oh, the deadline was moved up to last night, and I've got like a 36% on one of my lowest homeworks. And if you ever look at it,
I'll
I did get, yeah. If you look at it with the material, I did get a 92 on my first exam, which is, terrific. Yeah. So I'm learning it, but my overall homework score is like a 74.13. So
I see.
I was,
Yeah, I don't mind extending them. I don't. This semester, I'm trying to do everything I can to help everyone out, so that's fine.
that's fantastic. All right. Well, I got everything crammed in.
And if I don't do it, just keep bothering me about it.
Okay. I'll keep bothering you.
Like every day. Hey, extend it, asshole. Come on, something like that.
Okay.
Probably should have stopped recording, but anyways, what can you do?